All right, so this is a summary of those significant figures notes that we took in class, either for you to revisit them or if you were absent. And this is going to fill in page 10. There's kind of two separate parts where I'm going to have you go practice someplace else real quick before we come back and dig into these significant figures a little bit deeper. So let's go ahead and get started. And there wasn't exactly a place for this in the notes, but I wanted to start by defining significant figures. Those are just what the words sound like. Significant meaning important, figures being digits or numbers. So here we're going to be talking about how important numbers are in our measurement and which numbers are important versus other ones. And just in case you hear me slip up today as we're doing these notes, I'm mostly going to call these sig figs after today, after these notes. I really do think saying significant figures over and over again will help drive home what we're talking about, but it's kind of a mouthful, so in the future we will shorten this down and just call them sig figs in general. And when it comes down to it, better measuring devices have more significant figures. They give us more digits to make our measurements more precise and help us be more accurate in the long run. So we can look at any two pieces of equipment and compare how good of a measuring device they are by how many significant figures they're giving us. And even before we learn all about significant figures, looking at these two scales, you can tell that the one on the right is slightly better than the one on the left just because it gives us more digits there. So that's what this is all coming back to, is making sure we understand the importance of our measurements and what they mean for the calculations we're going to do with them. So let's look at the rules for what is a significant figure and what isn't. And the first rule is the biggest, most important, but also the simplest. If there's anything that's not a zero, it's always a significant figure. So 1, 2, 3, 4, 5, 6, 7, 8, 9, all sig figs, no matter what, no debate about it. So we can always count on things that aren't zeros. Zeros are going to be where our headache comes in, especially since there's 3 different types of zeros. So we're going to look at each of them individually, and I highly encourage you to highlight key information in these big blurbs of text so that you can come back and look and see leading zeros is what we call them. We can see that we highlight over at the other side there. They do not count as significant figures. Never. It's a hard and fast rule. Leading zeros are never significant. And we can see that example is highlighted 0.0025. All of those zeros are leading zeros. They're to the left of all of our other non-zero digits, the start of the number. And those zeros might seem important because without them, we wouldn't have 0.0025. We'd just have 25, which is a completely different number. But we can actually get rid of them if we use scientific notation, because all those zeros are doing there is holding the place value of the 2 and the 5. And we can hold that place value with this times 10 to the negative 3. We're going to learn a lot more about scientific notation in the days and weeks to come, but just showing you this to show you and remind you that we can actually get rid of those zeros there. And the great thing about scientific notation is it is specifically designed to help us get rid of the numbers that are not significant. So when we look at scientific notation later, this first number before the times 10 part is what we call the base. And that base is only going to have significant figures. If there are numbers that aren't significant, we don't keep them there. It helps us shorten things down, helps scientists be lazy, basically. Another example of a leading zero that just makes it a little more obvious how silly they are and how much we can do without them is if I put this 0 in front of that 25. You would never write 25 like that, and if you did, your math teacher might even come up to you and ask, like, why did you put that 0 there? You know it's not necessary. It just looks weird. There's never a leading zero that is significant, that's important enough to keep in that number no matter what. We can always get rid of them and still have that same level of significance in our number. Now, our second type of zeros are captive zeros, and these always count as significant figures. These are those zeros that are between other non-zero digits, like those 2 zeros you see in 1.008. They are always significant figures. I sometimes call these sandwiched zeros instead of captive zeros because they're sandwiched in between those other non-zero digits. But no matter what we call them, they are always significant, just like those non-zero digits. And then trailing zeros are zeros at the end of our number, and these are only sometimes significant. So leading zeros are never, captive zeros are always significant, and trailing zeros are sometimes. But all it depends on is a decimal point. If there's a decimal point anywhere in that number, the zeros at the end become significant. If there's no decimal, then those trailing zeros are not significant. And they show you that example with the 100 here versus the 100 with the decimal point. These are technically two different numbers with different levels of significance. Without the decimal, the trailing zeros are not significant, and that's just a 1 sig fig measurement. It's not very precise. These zeros here are significant because there's a decimal present, so that gives us a 3 significant figure number. So just by looking at these numbers, I can tell that this second 100 was made, this measurement was made on a better measuring device. So there's a couple other examples that I have of some trailing zeros just to try and hit home a point that I know a lot of people get confused on with these trailing zeros. Where the decimal is in the number does not matter one bit. So in that 100 example, adding the decimal at the end made those zeros significant. And that kind of makes sense because it's right there by the zeros. It almost like sandwiches those zeros with that 1 to make them significant. But it does not matter where the decimal is. That decimal could be in the middle of the zeros and it still makes them significant. It could be right in front of the zeros. They're still significant. It could be over here, not even touching those zeros, and the zeros are still significant. No matter how many numbers we squeeze between that decimal and those trailing zeros, if there is a decimal anywhere in the number, those trailing zeros at the very end of the number all become significant. So we'll do a couple of examples in order to help that hit home. And this process that I have written at the top of the page is probably not something that you need to stop, pause, and write down. This is a process I'm going to walk you through, but this should really be a process that happens in an instant. It shouldn't have to be something you go and look up and do step 1, and then step 2, and then step 3. But this is how we start the process and make sure that we're looking at these numbers correctly. I'm actually going to start with the second example here because knowing that we're looking for things that aren't zeros, this whole number is non-zero digits. And so there shouldn't be any debate about whether these are sig figs or not. They're all automatically significant figures. So all we got to do is count 1, 2, 3, 4 total numbers there. Means we have 4 significant figures in that number. Now in the rest of these that have zeros, we'll start by finding the non-zero digits, like this 1 up front, and then looking at where the zeros are in comparison with those non-zero digits is going to help us figure out whether they're significant or not. So these zeros at the end of this first example are after the 1, after all of the other non-zero digits. And that makes them what we called trailing zeros. And the rule for trailing zeros was that they are only significant if there's a decimal present, which there's not, which means these are not significant figures. So this number only has 1 significant figure in it, not a very precise measurement. Then down here in our next example, I find my non-zero digit, and these zeros are in a different place. Even though there's still zeros and a 1, these zeros are ahead of the 1. These are leading zeros. And leading zeros are never significant. So doesn't matter that there's a decimal there, doesn't matter how many there are before or after that decimal. Any zeros ahead of other non-zero digits are never significant figures. So this also has 1 sig fig in it. Next, we've got 2 non-zero digits in that 10,005 number. And because we've got those 2 digits on either side of the number, that means that these zeros are captive zeros or sandwiched zeros. And these are always, always, always significant. So in addition to the 1 and the 5, we've got these 3 zeros, which gives this number a total of 5 sig figs. And then in this last example, we've got a 1 up front, 3 trailing zeros after it, and trailing zeros depend on the decimal, and because there is a decimal present, these are also significant figures. So that gives this number 4 significant figures total. So hopefully those weren't too bad. We're just counting numbers, counting digits in numbers, and trying to decide whether they're all significant or not. And the rules might be a little bit weird, but the more you practice them, the more natural it'll become. And if you can take it step by step, like I've laid out in these green instructions at the top of the page, you can analyze any number. Now, I'm about to ask you to do a few on your own, but I want to do one more mixed problem because all of these other examples that I've done had one type of zero in them, but we can have multiple types of zeros. So let me write out an example. And if we look at this guy, we've got a lot of different zeros going on here, but it doesn't matter how many different types we have. If we start by finding our non-zero digits, then we have these 3 separate groupings of zeros, and we can look at them each individually. Over here, we've got these 2 zeros, which are in front of all of the other digits, all of the other sig figs, and that makes them leading zeros, and that means they are never significant figures. Then we have this 1 0 that's in the middle, our sandwich zero, and we know automatically that guy is going to be a significant figure. And then we've got our 0 at the end, our trailing 0, and I look over in that number and I do see a decimal point, so that is a significant figure. So looking at this, we've got a total of 1, 2, 3, 4, 5 significant figures in this number. So just take it slow, look at each of these examples that I'm going to ask you to do on this page 12 at the bottom. Just look at each of those separately, each of the groupings of zeros, and look back at your page 10 rules in order to figure out how many sig figs they each have. So give them your best shot. Maybe pause this here while you try them, because then we're going to go on to how we use these numbers in calculations. So we're not just counting things to count things. We're trying to figure out and be able to compare the different precision of different measurements, like what we were talking about at the start of this video. And if you think about trying to calculate a volume of something, volume we could calculate by taking the length times the width times the height of some object. Now, if I measure the length, the width, and the height really, really super carefully with lots of significant figures, then I would expect my volume to also be a very good measurement, or have lots of significant figures to reflect the measurements that were taken in order to get that value. In the same way, if I take some really kind of bad length, width, and height measurements, they're just approximations. Maybe I don't even use a ruler. I just look at it, I'm like, that looks like it's about this length, width, and height. Then I would expect the volume that I get from those kind of cruddy measurements to also be a kind of cruddy, less precise value, have less significant figures than if I'd used better measuring devices. So in that way, our significant figures in our answers are always going to have to match the significant figures that we start with. But what's going to happen more often than not is that we're going to have some different levels of significance, some different numbers of significant figures in our calculations. Like maybe I measured my length and my width super duper well, but my height was kind of just an approximation. Then my volume measurement, my volume calculation that comes from these numbers is only going to be able to be as precise and accurate as the worst measurement here. So this volume is not going to have as many significant figures as if I'd measured every one of those values, the original measurements, with the same level of precision there. So that's what we're hitting on here. So like I was just saying, when we combine numbers together, the answer will always be rounded based on the least precise measurement. But depending on whether we're doing multiplication or division, how we measure that least precise measurement is going to change slightly. In multiplication and division, we're going to be looking at significant figures. And the significant figures in our answer is going to be the same as the smallest or least significant figures from the numbers in the calculation. Our addition and subtraction, on the other hand, is going to look at the number of decimal places in the answer, and that's going to be determined by the least number of decimal places from the numbers in the calculation. So, this going back to those decimal places, because addition and subtraction really does change numbers in a slightly different way than multiplication and division, but that kind of gets technical. What you need to know is that sometimes we turn on the sig fig part of our brain when we're doing multiplication and division, and sometimes we look at decimal places. But either way, we're going to keep the least number overall as the numbers that we started with. And you've got a couple examples of each here that I'm going to touch on. So with this first example in the multiplication and division, we're doing 4.56 times 1.4, and I get the answer 6.38 out in my calculator. But that's not our final answer. This says that we're rounding our final answer to 6.4. And the reason for that is because my givens, the number I started with, this 4.56, had 3 significant figures, but my second number, 1.4, had 2 significant figures. And since we're rounding to the smallest, least precise measurement, then that means that I am going to have to round my answer down to 2 significant figures. So when we round according to significant figures, we just start from the left, move to the right, first significant figure in this number, second significant figure in this number, and then we round normally. The 8, which is the next digit, the first digit we're cutting off, gets a chance to change that last digit that we're trying to keep. So if that 8, that next number, is a 5 or more, it raises the score. It raises up that 3 to a 4, like what we saw happen here. If it's 4 or less, we just let it rest, and it wouldn't change that number that we're keeping. No matter what, it goes away, but it gets a chance to change that last number that we keep, no matter what. And that process for rounding is the same as what you've been doing in your math classes. It's just the words that I'm saying that sound a little bit different. In your math class, they would probably just tell you to go and round this to 1 decimal place, and you'd just be able to zero in on that 3 immediately and just look at the next digit. It would still raise that up. Your answer would be 6.4. They just have to tell you exactly what number to go and look at. The way that we do science and math calculations with science is that you use the original numbers that you put together to decide where to round your answer. You shouldn't have to ask me ever again, how should I round this? How many numbers should I keep? You just look at the significant figures and make that decision yourself. And then you just have to count from the left to get the correct number of significant figures instead of going straight to that one number. So not really that complicated, and I'll work with you if you're not quite getting this, but the process for rounding really should be the same. The wording is just a little bit different. And in this next example, when we're doing 9 divided by 3, the math is pretty simple. The calculator agrees the answer is 3. But if we look at that 3 is not a very precise 3. That's just, I've got about 3 there. There's only one significant figure in that number. And our original values that we started with, our measurements, had a lot more significant figures than that. So we want our answer to show the level of effort and measurement that we put into those original values. So looking at these numbers, we have 3 sig figs and 5 sig figs. Keeping the least number means that our answer should have 3 significant figures. So this is one of those times where it's weird, but we're actually adding significant figures to our number. The 0.00 gets this to become a 3 sig fig number, and that looks like a much better measurement than that original 3, and it just reflects the original measurement's significance. That addition and subtraction example that we've got at the bottom of the page is almost completely back to kind of normal rounding. You just don't have to be told where to round. We're adding together this 12.11 that has 2 decimal places in it, plus this 18.0 which just has one decimal place, and then 1.013, which has 3 decimal places. We put that all in our calculator and get a raw number out, and our final answer has to have the least number of decimal places from our original numbers that we were adding up. And our least number of decimal places was 1 decimal place in that 18.0. So we just come over to that first decimal place in our answer and round it to that point. So just like we talked about before, we look at the next digit, the first one we're cutting off, and the 2 gets a chance to round up the 1, but it can't, it doesn't. So they just end up going away, and our final answer is 31.1, just rounded to that first decimal place. So really what we need to be ready for is, when do we use sig figs versus when do we use decimal places? Most of the math we do is probably going to be multiplication and division, so most of it is going to be these new sig figs things. But occasionally we will do some addition and subtraction, so I want you to be aware of those rules. So a quick little side note before we do some math examples in your packet together is about exact numbers. Those exact numbers, which is the first space that you need to fill in, are numbers that we assume have an infinite number of significant figures. These are numbers that have been calculated or determined by ultra-precise counting or ultra-precise experiments over years and years, that we are 100% confident of this ratio. Like there's 60 seconds in a minute. Like it says right there in front of you, those numbers are just one significant figure each. I don't have to put 100 zeros after it to show that we are 100% sure that it's exactly 60, not 60.1 or even 60.01 seconds in 1 minute. It's 60.00000, an infinite number of zeros, exactly 60 seconds in exactly 1 minute. And so because those are exact, that frees us from having to actually write out all of these zeros just to show the level of effort and work we've put into calculating these numbers. That's not necessary. If we make or use a standard like this, then we can just look at these simpler, shorter numbers and understand, because it's a constant, we are not going to round our final answer based on that level of significant figures that we physically see for that exact number. Another example that would always be an exact number is if we're counting things like on your hands, not using a measuring device. That is an exact, super precise measurement, because you know 100% certainty that there is that many things there, especially when it comes to like counting people. If I tell you that there's 30 students in this room, I shouldn't have to say that there's 30.0 students in this room. We should all assume that there's not 30.1 students in that room. We know that. We understand that. I shouldn't have to tell you 0.0 for you to trust and be assured that there's not 0.1 students being hidden in a closet or a cabinet someplace. That exact counted value is an exact number, which gives it infinite significant figures. Other things that we've defined relationships as, like 1 foot equals 12 inches, just like the 60 seconds in 1 minute. These are infinite sig figs, even if it doesn't look like it, because that's the way these units were defined. So we'll talk more about those when we do more conversions and see some more exact numbers. But let's look at some calculation examples. And you're probably going to have to take a second and pause the video here in order to write down questions 2 and 3. I really do want you to see the math that's going to get us these answers, which we're about to round. But unfortunately, those fancy equations did not pop up in time to get printed out with the rest of the packet. So you're going to have to write those down. Feel free to write these raw numbers straight out of the calculator or not. The real important part is that you get the next numbers that pop up on the screen, which are the final rounded answers. But I like to show both so that you can see that transition. The original number, you can put it in your calculator, confirm that you're able to do that math and understand why and how we round these things. So here in this first calculation, we're doing 5.00 times 6.00. And that is multiplication, even though we don't see a multiplication sign. And our calculator tells us that 5 times 6 is 30. But if we look at these significant figures, because this is multiplication, we care about significant figures, not decimal places. And I should have just written sig figs in order to keep that short. We need to count the significant figures in our original numbers. This has 4, this has 3, and then we need to keep the least number of significant figures in our answer. So we need to make our answer have 3 sig figs. But there's only 2 numbers. I guess if I need 3 significant figures, I'm going to have to add a number. The only number that I can add without changing this value is a 0. So we're going to add that 0.0 at the end. As soon as I add the decimal, that makes that trailing 0 significant. And then I add another trailing 0 to give us a total of 3 that we were looking for. Then in the next problem, we got a lot of numbers here, but it's still just multiplication and division happening all together. But that still means that we're looking at the number of sig figs in each of these values in order to figure out how many sig figs should go in our final answer. And almost all of those numbers have 4 significant figures in them, except for that last one has 3. But it only takes one measurement. If this is what my least number of significant figures is, then my answer needs to be rounded to just keep those first 3 significant figures, not all the rest of those numbers. Now, this is something kind of weird and different that I wanted to point out and make happen here, because if I just kept 3 numbers, if I just wrote down 532 and thought that I was rounding that off to 3 significant figures and done, this would not be anywhere close to the correct answer. You've written down 3 digits, but you haven't rounded it to those 3 significant figures. You've just cut off everything else. 532,324.7979 cannot just get rounded to 532. If your math teacher was telling you to round this number, the words they would probably use if they wanted you to round this here at that 2's place, that's the thousands place, they would tell you round this number to the nearest 1,000. And you'd come here and you'd look at this and be like, okay, well, is this closer to 532,000 or is it 533,000? And it is definitely closer to 532,000. We have to fill in these spaces here between the significant figures we want to keep and that decimal place with zeros. And you might even go ahead and make a note of that, because that's something that people struggle with sometimes. The fact that I'm asking you for 3 sig figs, but you are able to still write down more than just 3 digits as long as the zeros that you're writing down don't have a decimal anywhere in that number, then those are not significant zeros. So those are going to help us round and keep the place value of the numbers that we're keeping without adding any significant figures. So zeros not being significant can help us. Now, in this next problem, we do have some division happening, and there's actually no multiplication, even though it looks like it. This is a scientific notation number down here at the bottom. So, just looking at the number of sig figs in our top number and our bottom number, that looks like that's going to be 5 and 3, because remember, with scientific notation, everything before that times 10 stuff is a significant figure. Then my answer should be rounded to 3 sig figs, which means I want to keep these 2, 7, and 9. The number right after the 9 is not big enough to change the 9. So that's just going to stay as 2, 7, 9. I'm going to clean this up a little bit and get some of those nice answers there so that we can move on with a fresh start to this last problem here, where finally we're doing some addition, which means we're not actually going to pay attention to sig figs here. We're going to be counting and comparing the decimal places in each of these numbers as well as our answer. So my first number here only has 1 digit past the decimal, 1 decimal place. Here our second number has 2. So if we're keeping the least number of decimal places, that means that we should only keep one decimal place in our final answer. So I want to round this to that first decimal place, which means the 7 does get that chance to round the 3 up to a 4. So those are all of those examples, and I actually have one more for you. I'm going to pose you kind of a real life question. If I have a box that says it's got 100 paper clips in it, and I want to divide that box of paper clips into 3 stacks, 3 groups are going to be sharing these paper clips. How many paper clips are going to be in each stack given to each group? Because you can probably do this math and think about what the answer would be straight out of the calculator, or even grab a calculator and find that answer. But make sure that you're paying attention to the sig figs in these numbers, and the level of accuracy and precision that we start with is going to be reflected in the accuracy and precision of the answer to this real life, very reasonable question. So if you want to check your answer with me or talk about that last problem or any of the problems in here, please come and see me. Please ask me. These are something that's going to follow us through the rest of the year, so we need to get some of these basics down, and I don't want you to struggle with them on your own. So come and see me and I'll help you out with it. Now, the practice that goes along with what we just did here in our packet is page 13 at the top. We're only going to do that left-hand side, and the right-hand side is completely optional. I've posted the answers to them just so that you can check that right side and make sure that you're doing things right, and maybe give you a little extra confidence with what you've done on the left side. So work on those left side problems. Come to me if you have any questions.